Look up at the night sky, and what do you see? A scattering of stars, maybe a planet or two. But what if I told you that everything visible to the naked eye is just the tiniest fraction of what's really out there? Beyond those familiar points of light lies a universe so vast, so unimaginably enormous, that it defies everything we know about scale. Think about the tallest mountain on Earth, the deepest ocean, the grandest canyon. Now imagine structures so colossal they could swallow all of them 1,000,000 times over and still have room to spare. That's the reality of the largest formations in our galaxy, cosmic titans lurking in the darkness, waiting to rewrite everything we thought we understood about size, distance, and even time itself. What makes these galactic giants so awe-inspiring isn't just their sheer scale. It's how they challenge our very perception of reality. Picture a bubble so massive it could hold thousands of solar systems, or a ring of stars stretching so wide that light takes tens of thousands of years just to cross it. These aren't science fiction, they're real, they're out there, and they're so immense that if you tried to build a model of one, even using the entire Earth as a starting point, you'd still fall hopelessly short. And yet, against all odds, humanity has somehow managed to find them, study them, and piece together their secrets, each discovery peeling back another layer of the universe's grand design. That's exactly what we're diving into today. 25 mind-bending facts about the largest structures in our galaxy, each one more astonishing than the last. From supermassive black holes with gravitational pulls so strong they warp space itself, to cosmic filaments so long they stitch entire clusters of galaxies together, this is where the ordinary ends and the extraordinary begins. So if you've ever stared up at the stars and wondered what else is hiding in that infinite darkness, get ready. By the time we're done, you'll never look at the night sky the same way again. The universe isn't just a random scattering of galaxies, it's a meticulously woven tapestry. A vast interconnected network so colossal, it makes even the grandest cosmic structures seem tiny in comparison. Scientists call this the cosmic web, and it's the largest known arrangement of matter in existence. Picture an enormous spiderweb stretching across the cosmos, its threads woven not from silk but from galaxies, gas, and dark matter, all bound together by gravity over billions of years. These filaments can span hundreds of millions of light years, forming bridges between galaxy clusters so distant they defy comprehension. To grasp just how immense this structure is, imagine shrinking the entire Milky Way galaxy down to the size of a grain of sand. Even at that scale, the cosmic web would still stretch for miles in every direction, an intricate lattice of unimaginable scale. What's even more astonishing is that we're not just passive observers of this web, we're part of it. Our own galaxy, along with every star we see in the night sky, sits embedded within one of these filaments, like a single strand in a cosmic spider's masterpiece. And here's what really bends the mind. The cosmic web isn't static. It's a dynamic, evolving structure shaped by the invisible hand of dark matter, its filaments slowly pulling galaxies closer together while the expansion of the universe stretches them apart. It's a cosmic tug-of-war playing out over eons, with the web itself acting as both the battlefield and the prize. This isn't just a curiosity, it's the backbone of the universe, the scaffolding upon which everything we know is built. Without it, galaxies wouldn't cluster, stars wouldn't form, and the night sky would be a far emptier place. So the next time you gaze up at the stars, remember, you're not just looking at distant points of light. You're seeing the threads of the universe itself. But how big is too big when it comes to cosmic structures? The Hercules-Corona Borealis Great Wall forces us to completely rethink that question. This mind-boggling formation holds the record as the largest single structure we've ever discovered in the observable universe, a staggering 10 billion light-years across. To put that impossible scale into perspective, if you could travel at the speed of light, it would take you twice the current age of Earth just to cross from one end to the other. That's not just big, it's universe-redefining big. When astronomers first mapped this behemoth in 2013, it sent shockwaves through the scientific community. According to long-standing cosmological principles, there's supposed to be a theoretical limit to how large structures can grow, a cosmic speed bump created by the universe's expansion and the finite time since the Big Bang. The Hercules-Corona Borealis Great Wall doesn't just ignore that limit, it shatters it completely. Imagine building a sandcastle so tall it defies gravity itself, and you'll start to grasp how this structure upended everything we thought we knew about the rules of cosmic architecture. Its name comes from two constellations it stretches between: Hercules, the legendary strongman of Greek myth, and Corona Borealis, the celestial crown. There's something poetic about that pairing, a structure so powerful it bends the laws of physics, named after figures symbolizing unbreakable strength and royal grandeur. But this isn't some solid wall like you might picture. It's an immense filament of galaxies, galaxy clusters, and dark matter, woven together by gravity over billions of years. Seen from afar, it resembles a faint, ghostly highway stretching across the cosmos, with entire galactic superclusters strung along its length like glowing streetlights. What makes this cosmic titan even more fascinating is how we found it. Unlike nearby structures we can observe directly, the Hercules-Corona Borealis Great Wall revealed itself through gamma-ray bursts, brief, violent flashes of energy marking the deaths of massive stars. These cosmic fireworks acted like breadcrumbs, allowing astronomers to trace the invisible scaffolding of matter connecting them. It's as if the universe left us a trail of glowing clues in the darkness, each one pointing toward something far greater than we ever imagined could exist. And here's the haunting part: we don't even know if this is the universe's final size record. As our telescopes peer deeper and our detection methods improve, who's to say we won't find something even more colossal lurking in the shadows? The Hercules-Corona Borealis Great Wall isn't just a scientific curiosity, it's a humbling reminder that no matter how much we learn, the cosmos always has another surprise waiting. If the Hercules-Corona Borealis Great Wall feels unfathomably vast, prepare to meet its slightly smaller but no less astonishing cousin, the Sloan Great Wall. Clocking in at 1.4 billion light-years across, this galactic behemoth holds the title for the second largest known structure in the observable universe. To put that into perspective, if our Milky Way were the size of a marble, the Sloan Great Wall would stretch from New York to Los Angeles repeatedly. And yet, what makes this structure truly remarkable isn't just its size, but the intricate cosmic ballet it reveals about how the universe organizes itself on the grandest scales. Discovered in 2003 by astronomers analyzing data from the Sloan Digital Sky Survey, this colossal filament isn't some random scattering of galaxies, it's a carefully woven ribbon of superclusters, dark matter, and glowing gas, all strung together like pearls on an invisible string. The survey's painstaking mapping revealed something extraordinary. The wall isn't just a flat, two-dimensional structure. It twists and turns through space in 3 dimensions, forming a complex, interconnected web of galactic neighborhoods. Imagine looking at a crumpled sheet of paper under a microscope, only to realize each tiny ridge is a highway of stars millions of light-years long. What's even more fascinating is how the Sloan Great Wall stacks up against our local cosmic landmarks. Our own galactic backyard, the Laniakea supercluster, a sprawling collection of galaxies including the Milky Way, spans a mere 500 million light-years. That means this wall is nearly 3 times longer than the entire supercluster we call home. It's like comparing a neighborhood block to a continent. And yet, despite its staggering proportions, the Sloan Great Wall isn't some impenetrable barrier. It's more like a backbone, a gravitational scaffold that shapes the flow of galaxies, guiding them along its length like cosmic rivers pulled by an unseen current. The real magic lies in how structures like this form in the first place. over billions of years, the subtle tug of gravity amplifies tiny fluctuations in the early universe, drawing matter into vast sheets and filaments. The Sloan Great Wall is essentially a fossil, a preserved imprint of the universe's adolescence, frozen in time and space. By studying its intricate folds and knots, astronomers can trace the universe's growth like rings in a tree trunk, decoding the hidden history written in the distribution of galaxies. But here's the humbling twist. Even a structure this immense is just one thread in the grand tapestry of the cosmic web. It's a reminder that no matter how large something seems, the universe always has a way of putting it into perspective. The Sloan Great Wall doesn't just challenge our understanding of scale, it invites us to rethink our place in the cosmos. We're not just tiny specks floating in emptiness, we're part of a vast, dynamic architecture, one that connects every star, every galaxy, and every wall across the endless expanse of space. Now let's zoom in from those unimaginably vast cosmic walls to our own galactic neighborhood, the Laniakea supercluster. While it might seem modest compared to the billion light-year giants we've been exploring, don't let its relatively smaller size fool you. Spanning 520 million light-years and containing over 100,000 galaxies, including our very own Milky Way, Laniakea is less like a neighborhood and more like an entire celestial continent. The name says it all. Borrowed from Hawaiian, it translates to immeasurable heaven, a fitting title for the sprawling cosmic metropolis we call home. What makes Laniakea truly special isn't just its scale, but how it redefined our understanding of local cosmic geography. Before its discovery in 2014, astronomers typically mapped the universe by focusing on visible galaxy clusters. But Laniakea revealed something far more profound: the hidden gravitational currents that orchestrate the motion of galaxies across unfathomable distances. Imagine staring at a river and seeing only the floating leaves, then suddenly realizing the powerful underwater current guiding them all. That's the breakthrough Laniakea provided. At the heart of this supercluster lies the Great Attractor, a mysterious gravitational focal point pulling everything in Laniakea toward it. Picture a cosmic whirlpool with galaxies like ours caught in its slow but relentless flow. Our Milky Way might seem stationary, but in reality, it's sailing through this gravitational river at over 600 kilometers per second, a speed that would get you from Earth to the Moon in just 10 minutes. Yet here's the twist: even at that blistering pace, we're barely making progress on the supercluster's scale. It would still take tens of billions of years to reach the Great Attractor. Visualizing Laniakea is like mapping an archipelago in an ocean of emptiness. The galaxies within it aren't scattered randomly, they're threaded along delicate filaments, clustering at intersections like cities along highways. Our Milky Way sits near the edge of one such filament, a minor suburb in this grand celestial metropolis. And just as city lights fade into rural darkness, the density of galaxies thins out at Laniakea's borders, where the gravitational pull of neighboring superclusters begins to take over. What's truly humbling is realizing that everything we've ever known, every star visible to the naked eye, every planet we've discovered exists within this single supercluster. Laniakea doesn't just contain us, it shapes our cosmic destiny, guiding the Milky Way's path through the universe with the same inevitability as a leaf caught in a gentle current. So the next time you gaze up at the night sky, remember, you're not just looking at stars, you're seeing the glowing skyline of our immeasurable heaven. Just when we thought we'd encountered the limits of cosmic scale, the universe delivers another staggering surprise: the giant arc. Stretching an incomprehensible 3.3 billion light-years across the distant universe, this vast crescent of galaxies isn't just breaking records, it's bending the rules of cosmology itself. Discovered in 2021 by a team analyzing light from distant quasars, this structure shouldn't exist according to our current understanding of the universe's evolution. Its very presence throws a wrench into long-held assumptions about how matter distributes itself across the cosmos. What makes the giant arc so extraordinary isn't merely its size, it's the elegant, almost artistic curve of its formation. Picture a rainbow painted on the fabric of the universe, but instead of water droplets refracting light, this arch consists of galaxies, galaxy clusters, and vast clouds of gas, all tracing a graceful path across the sky. If you could see it with the naked eye from Earth, it would span the width of 20 full moons, an impossible feat given its staggering distance of 9.2 billion light-years away. That means we're seeing it as it existed when the universe was just half its current age, a fossilized imprint of the early cosmos. The real controversy lies in what the giant arc implies about the universe's structure. Cosmologists operate on something called the cosmological principle, the idea that, on large enough scales, matter should be evenly distributed. But this crescent-shaped behemoth defies that expectation dramatically. Imagine shaking a snow globe and watching the flakes arrange themselves into a perfect spiral instead of scattering randomly. That's the level of peculiarity we're dealing with here. Some theorists argue it might be evidence of exotic physics we don't yet understand, perhaps relics from the universe's explosive birth. Others suggest it could reveal flaws in how we model the distribution of dark matter, the invisible scaffolding shaping cosmic growth. Debates about the giant arc's significance rage through astronomy conferences and research papers. One camp sees it as a statistical fluke, a chance alignment of galaxies that only appears coherent from our vantage point. But the odds of such an alignment happening randomly are astronomically low, roughly 1 in 20,000. Another faction proposes it might be the visible imprint of primordial sound waves from the Big Bang, frozen in time and stretched to impossible proportions by the universe's expansion. Then there's the most radical possibility that we're seeing evidence of cosmic strings, hypothetical defects in spacetime left over from the universe's formation, predicted by some theories but never directly observed. What's truly humbling is realizing we're essentially cosmic detectives, piecing together clues from light that's been traveling for over 9 billion years. The giant arc doesn't just challenge textbooks, it invites us to reconsider fundamental questions about how structure emerges in the universe. Is the cosmological principle incomplete? Are there even larger patterns waiting to be discovered? Every time we push the boundaries of our telescopes and simulations, the universe responds with new mysteries that are grander and more perplexing than anything we dared to imagine. For now, the giant arc stands as both a triumph of discovery and a riddle wrapped in starlight. Whether it ultimately reshapes our understanding of cosmology or becomes a curious exception to the rules, one thing is certain: the universe still has plenty of surprises up its sleeve. And that's what makes the search so thrilling. While the universe is often imagined as packed with galaxies, stars, and cosmic wonders, there exists a place so eerily empty it defies intuition: the Bootes Void. Spanning a staggering 330 million light-years, this spherical region of near-nothingness is so vast that if our Milky Way sat at its center, the next nearest galaxy would be almost unimaginably distant. Dubbed the Great Nothing by astronomers, it's one of the largest known voids in the observable universe, a gaping hole in the cosmic web where matter seems to have simply vanished. But here's the paradox: emptiness this extreme is just as vital to the universe's structure as the glittering filaments of the cosmic web. Think of the universe as a slice of Swiss cheese. The dense regions where galaxies cluster are the cheese, while voids like Bootes are the holes. Without these vast, empty spaces, the web couldn't maintain its delicate balance. Gravity needs room to work, pulling matter into filaments while leaving behind these cavernous bubbles. The Bootes Void isn't a mistake, it's a necessary counterweight to the universe's crowded neighborhoods. What makes this void especially haunting is just how deserted it truly is. While most cosmic voids still contain a handful of galaxies, the Bootes Void holds only 60 or so in its incomprehensible volume. a number so low, it's like finding a single grain of sand in an Olympic-sized swimming pool. The few galaxies that do linger here are likely runaways, ejected from the chaotic dance of galactic collisions eons ago, now drifting in lonely exile. Imagine standing in the middle of an endless desert where the closest town is so far away, light from its streets would take millions of years to reach you. That's the isolation of a galaxy trapped in the Bootes Void. The void's discovery in the 1980s sent shockwaves through astronomy. While mapping galaxy distributions, astronomer Robert Kirshner and his team stumbled upon this bizarre blank spot, a region where telescopes expected to find thousands of galaxies but instead saw almost nothing. At first, some theorized it might be an observational glitch, a place where interstellar dust blocked our view. But as technology improved, the truth became undeniable. The void was real and its emptiness was profound. What's even stranger is how the Bootes Void challenges our understanding of cosmic evolution. According to standard models, the universe's matter should distribute somewhat evenly over vast scales. Yet here's a place where that rule collapses spectacularly. Some theorists speculated could be evidence of an ancient collision with a parallel universe, or the imprint of exotic physics from the Big Bang we don't yet comprehend. Others suggest it's simply a statistical fluke, a natural if extreme variation in the cosmic web's weave, but perhaps the most unsettling thought of all. The Bootes Void isn't alone. Scattered across the cosmos are countless other voids, some nearly as large, weaving their emptiness between the galaxies. They remind us that the universe isn't just about what's present, it's equally defined by what's missing. For all our fascination with cosmic giants and glittering structures, these absences hold their own mysteries, silent and vast, shaping the universe as surely as the brightest star. Swimming through the cosmic ocean like some celestial leviathan, the Pisces-Cetus supercluster complex stretches a jaw-dropping 1 billion light-years across the universe, a sprawling network of galaxies so vast it makes our entire local group feel like a speck of dust. Named for its resemblance to both a fish and a whale when mapped in 3 dimensions, this gargantuan structure isn't just another cluster of galaxies. It's an interwoven tapestry of galactic filaments, each one brimming with thousands of galaxies bound together by the invisible threads of gravity. Imagine throwing a net into the cosmos and pulling up not just a few scattered stars, but entire galactic neighborhoods intertwined like knots in a cosmic fishing line. What makes this supercluster complex truly special is its sheer complexity. Unlike the relatively flat walls we've explored earlier, Pisces-Cetus twists and undulates through space, forming a 3-dimensional labyrinth of star-filled tendrils. Deep sky surveys reveal its structure with startling clarity, long, luminous filaments arcing between dense galaxy clusters, creating a shape that, when viewed from the right angle, eerily mirrors the silhouette of a whale chasing a fish through the void. It's as if the universe itself decided to leave a signature in the stars, a playful nod to the myths of sea creatures that ancient civilizations once projected onto the night sky. Zooming into one of these filaments reveals something even more extraordinary. Each one acts like a cosmic highway, with galaxies streaming along its length like cars in slow motion, drawn toward massive gravitational anchors, superclusters with names like Perseus, Pisces, and Cetus that act as hubs in this celestial transit system. Our own Milky Way sits on the fringes of this complex, a tiny island near the edge of an immense archipelago. The scale is so vast that if you could hop aboard a spaceship traveling at light speed, it would take you 30,000 times longer to cross Pisces-Cetus than it has taken humanity to evolve from its earliest ancestors. But here's where it gets even wilder. Pisces-Cetus isn't just a static sculpture frozen in space. It's a dynamic, evolving structure, with galaxies slowly migrating along its filaments over billions of years, pulled by the irresistible tug of dark matter. Computer simulations show these filaments vibrating like plucked strings, resonating with the gravitational echoes of ancient collisions and mergers. Some astronomers compare it to watching a time lapse of a growing root system, each new branch representing another chapter in the universe's expansion, each knot of galaxies a snapshot of cosmic history in the making. The most mind-bending part, we're only seeing a fraction of the full picture. Because light takes time to travel, the deeper we peer into Pisces Cetus, the further back in time we're looking. The galaxies at its farthest edges appear as they were when the universe was barely half its current age, their light just now reaching us after an epic journey across the ages. This makes the supercluster complex not just a structure in space, but a living timeline of cosmic evolution, offering astronomers a unique window into how the universe grew from a smooth soup of matter into the intricate web we see today. So the next time you hear about superclusters, remember, they're not just random collections of galaxies. They're the universe's grand architecture, sculpted over eons by gravity's patient hand, and Pisces Cetus, with its twisting oceanic majesty, stands as one of the most spectacular examples of all. Deep in the heart of our cosmic neighborhood, an invisible force tugs at everything around it, the Great Attractor, a gravitational enigma so powerful it bends the paths of entire galaxies, including our own Milky Way. Hidden behind what astronomers call the zone of avoidance, a region obscured by the dense gas and dust of our galaxy's central plane, this mysterious anomaly has eluded direct observation for decades. Yet its influence is undeniable, pulling thousands of galaxies toward it with the irresistible grip of a cosmic magnet. X-ray and infrared telescopes have peeled back the veil, revealing a dense cluster of galaxies roughly 250 million light-years away, locked in a gravitational dance around something far more massive. Current estimates suggest the Great Attractor's pull comes from a concentration of matter equivalent to tens of thousands of Milky Ways. But here's the twist: it might not be the final destination. Recent studies suggest an even larger force lies beyond it, the Shapley supercluster, a behemoth 8 times more massive, acting like a grand conductor orchestrating the motion of galaxies across hundreds of millions of light-years. The real challenge in studying this cosmic mystery lies in its hiding place. Imagine trying to spot a lighthouse through a dense fog. That's the frustration astronomers face when observing the Great Attractor through the Milky Way's obscuring band. Infrared surveys like those conducted by the Spitzer Space Telescope and X-ray observatories like Chandra have been game changers, piercing through the cosmic clutter to map the unseen structure. What they've found is a sprawling confluence of galaxy clusters, vast clouds of hot gas, and most intriguingly hints of dark matter weaving it all together. What makes the Great Attractor so fascinating isn't just its hidden location, it's the questions it raises about our place in the universe. For billions of years, galaxies have been flowing toward it in a slow-motion river of stars, a phenomenon dubbed dark flow. Our own galaxy is caught in this current, racing toward the Great Attractor at over 2 million kilometers per hour. Yet paradoxically, we'll never reach it. The expansion of the universe stretches space faster than gravity can pull us in, leaving us forever chasing a destination that retreats as we approach. Ongoing research is unraveling this cosmic tug-of-war, with radio telescopes like the Square Kilometre Array poised to map the Great Attractor's influence in unprecedented detail. Some theories propose it might be a rare hypercluster of galaxies, while others speculate about exotic physics or even primordial flaws in spacetime itself. One thing is certain: as long as it hides behind the Milky Way's dusty curtain, the Great Attractor will remain one of the universe's most tantalizing puzzles, a reminder that even in our own backyard, the cosmos keeps its deepest secrets just out of sight. Back in 1989, astronomers made a discovery that shattered our cosmic perspective: the CFA2 Great Wall, a behemoth of galaxies stretching 500 million light-years across the universe. Until then, scientists assumed galaxies were scattered randomly through space, But this vast filament, named after the Harvard-Smithsonian Center for Astrophysics team that found it, revealed something shocking. The universe wasn't just a starry void. It had structure, bones, a hidden architecture written in the language of gravity and dark matter. The CFA2 wall didn't just break records, it rewrote the astronomy playbook. Imagine being the first person to stumble upon the ruins of an ancient civilization, realizing those scattered stones were actually part of a sprawling, interconnected city. That's how radical this discovery felt. By meticulously mapping galaxy positions using redshift data, the team uncovered a previously invisible backbone, a dense ribbon of galaxies so vast it made our own local supercluster look like a side street. Suddenly, the universe wasn't just stars sprinkled in emptiness. It was a web with galaxies clustering along threads like pearls on a necklace. What made this wall so revolutionary wasn't just its scale, it was how it shaped our understanding of cosmic evolution. Before its discovery, the leading theories suggested matter should distribute relatively evenly across space. But the CFA2 Great Wall proved the universe preferred clumps and filaments, a pattern that echoed through later discoveries like the cosmic web. Think of it like pouring pancake batter onto a griddle instead of spreading smoothly. It forms irregular bubbles and edges. The wall was our first glimpse of this universal tendency, revealing how gravity sculpted the cosmos over billions of years. Diving deeper, the wall's structure held even more surprises. Unlike later discovered walls that curve or twist, the CFA2 Great Wall was remarkably flat, a sheer cliff of galaxies towering over the cosmic plains. Some sections were so densely packed they contained thousands of times the mass of our Milky Way, while other regions showed eerie voids, as if some cosmic hand had swept entire sectors clean. This patchwork hinted at violent histories, ancient collisions, mergers, and tidal forces that left scars across the galactic landscape. Perhaps most astonishing was realizing how long this cosmic landmark had gone unnoticed. It wasn't hiding in some distant corner of the universe. It sat just 650 million light-years away, practically our backyard in galactic terms. The reason we missed it, we hadn't been looking at the big picture. Early galaxy surveys focused on small patches of sky, like trying to map a mountain range through a keyhole. The CFA2 Great Wall only revealed itself when astronomers stepped back, compiling thousands of observations into a single, sweeping atlas of the heavens. Today, the wall stands as a testament to how much we still have to learn about the universe's grand design. Later discoveries, like the Sloan Great Wall or the Hercules-Corona Borealis structure, may dwarf it in size, but none can match its legacy. It was the crack in the cosmic egg, the first glimpse of the hidden order beneath the chaos. And as we'll see next, it was just the beginning of a much bigger story. Hidden behind the Milky Way's dazzling disk, a cosmic leviathan lurks in our blind spot, the South Pole Wall. Stretching 1.4 billion light-years across the southern celestial hemisphere, this recently discovered behemoth ranks among the largest contiguous structures ever mapped. Yet it remained invisible until astronomers developed ingenious new ways to see through our galaxy's obscuring dust. What makes this discovery extraordinary isn't just the wall's staggering scale, it's the technological wizardry that finally brought it into view. Traditional galaxy mapping hit a brick wall literally when trying to observe regions behind our own galaxy's dense central plane. Imagine trying to study a mountainside while standing in a fog bank. That's the challenge astronomers faced. The breakthrough came when teams combined two cutting-edge techniques: redshift measurements to calculate galaxy distances and peculiar velocity mapping to trace their movements through space. By analyzing how galaxies subtly tugged on each other's motions, researchers could infer the presence of hidden mass, like detecting an invisible magnet by watching how it bends the path of iron filings. The resulting three-dimensional map revealed a structure so vast it redefines our local cosmic geography. Picture a continental shelf underwater, its outline only visible through sonar. That's how the South Pole Wall emerged from the data. This isn't some abstract collection of galaxies. It's a gravitational titan shaping the flow of our cosmic neighborhood. The wall's pull influences everything from the motion of our local group to distant galaxy clusters hundreds of millions of light years away. What's particularly fascinating is how this discovery upends assumptions about where massive structures should exist. Conventional models predicted large-scale matter distribution would be relatively uniform beyond our immediate vicinity. Yet here sits the South Pole Wall, a galactic Great Wall of China curving along the universe's southern frontier, its sheer size forcing cosmologists to reconsider how matter clumps together across the grandest scales. Some researchers speculate it might connect to even larger structures, forming a cosmic superhighway we've only begun to trace. The wall's discovery also highlights a profound truth about astronomy. Sometimes the most groundbreaking finds aren't made by looking farther, but by learning to see differently. Those same dusty regions that once frustrated observers have become treasure maps, their obscured galaxies now revealed through infrared eyes and gravitational inferences. As our tools grow sharper, who knows what other giants might be hiding in plain sight, waiting for the right technological key to unlock their secrets. One thing's certain, the South Pole Wall proves our cosmic backyard still holds monumental surprises. Far from being an average patch of universe, we're floating in the shadow of a colossus, one that's been quietly shaping galactic destinies since long before humans first looked up at the stars. Here's something that might make you see our galaxy in a whole new light. We're floating in one of the universe's emptiest neighborhoods. The KBC Void, named after astronomers Keenan, Barger, and Cowie, who identified it in 2013, is a staggering 2 billion light-year wide bubble of near-nothingness. And guess what? The Milky Way sits right at its heart. This isn't just a cosmic curiosity, it's a revelation that fundamentally reshapes how we interpret the universe's expansion and our place within it. Picture standing in the middle of an endless foggy plain where the closest landmarks are so distant they're barely visible. That's essentially our situation. While most galaxies cluster along the cosmic web's dense filaments, we're stuck in what astronomers call a local void, a region where matter is sparser than almost anywhere else. The KBC Void isn't completely empty. It contains our local group and a few other galactic stragglers, but compared to the bustling superclusters beyond its edges, it's eerily deserted. If the universe were a city, we'd be living in the equivalent of a remote countryside village, far from the bright lights and crowded streets. This unusual address has major implications for one of cosmology's biggest puzzles, the Hubble constant, the rate at which the universe expands. Measurements of this value keep clashing. Some methods suggest a faster expansion, others slower. The KBC Void might explain why. Here's the twist: emptiness affects gravity's pull. With fewer galaxies nearby tugging at us, the Milky Way and our neighbors drift outward faster than regions drowning in dense matter. It's like being in a boat with weak currents versus fighting a roaring river. We're getting pushed outward more easily, skewing our local measurements of cosmic expansion. But the real shocker, we might have vastly underestimated the void's size. Recent studies suggest the KBC Void could be even larger than initial estimates, a true cosmic underdog dwarfing most other known voids. That means our rural cosmic address might be more like living in a deserted continent. And because we're inside it, we've been like fish trying to describe water, unaware of how profoundly our sparse surroundings color our observations. The KBC Void isn't just a blank space, it's a lens distorting our view of the cosmos. For decades, astronomers assumed we lived in a fairly average patch of universe. Now we know better. This humbling realization forces us to recalculate not just distances, but the very yardsticks we use to measure the universe's growth. Every time we peer deeper into space, we're reminded, perspective is everything, and sometimes the most important discoveries aren't about what's out there, but about where we're standing. Hanging in the southern skies like a celestial chandelier, the Horologium Reticulum supercluster dazzles not just by its sheer size, spanning 550 million light-years, but by its staggering density. This southern hemisphere titan packs more raw cosmic power in its sprawling structure than entire galactic neighborhoods. Named after two constellations it bridges, the Horologium the Clock and Reticulum the Net, this supercluster lives up to both monikers, acting as a precise timekeeper of the universe's evolution while ensnaring galaxies in a gravitational web of unimaginable scale. What sets this supercluster apart isn't just its width, it's the jaw-dropping concentration of galaxy clusters packed into its framework. Imagine a cosmic metropolis where skyscrapers aren't buildings but entire clusters, each containing thousands of galaxies bound together by gravity. The Abell cluster's dense knots of galaxies like Abell 3266 anchor this structure, their collective mass warping spacetime so profoundly that light itself bends around them. And here's the kicker: visible galaxies only account for a fraction of the supercluster's heft. The real heavyweight, dark matter, weaving through the voids between galaxies like invisible scaffolding, amplifying the gravitational pull that keeps this cosmic city from flying apart. Peering into Horologium Reticulum is like stepping into a hall of mirrors reflecting the universe's most violent phenomena. At its core lies one of the hottest known galaxy clusters, where temperatures exceed 100 million degrees, so searing that gas clouds glow not with visible light, but with X-rays detectable only by space telescopes like Chandra. Collisions between galaxy clusters here release energy surpassing 1 billion supernovas, sending shockwaves rippling through intergalactic space for millions of light-years. These aren't just random crashes, they're the supercluster's construction crews, merging smaller groups into ever larger clusters in a slow-motion ballet choreographed over cosmic epochs. The supercluster holds another surprise: its peculiar motion. While most structures drift with the universe's expansion, Horologium Reticulum exhibits a dark flow, a mysterious, collective movement toward some unseen attractor beyond our current maps. This motion suggests an even grander structure lurking in the cosmic shadows, its gravity tugging at the supercluster like a hidden puppeteer. Some theorists speculate it could be connected to the Shapley supercluster, the universe's most massive known concentration of matter, but confirming that would require mapping regions currently obscured by our own galaxy's bulk. Perhaps most fascinating is how this southern giant challenges our understanding of cosmic evolution. Computer simulations struggle to replicate its intricate filamentary structure. The threads of galaxies and gas twisting through it resemble a spiderweb after a storm, asymmetrical and unpredictable. This isn't the neat, uniform distribution many models predict, hinting that our theories might be missing crucial physics, possibly related to dark energy's role in shaping the large-scale universe. For astronomers, Horologium Reticulum serves as both laboratory and time machine. Its most distant galaxies appear as they were 7 billion years ago, allowing us to witness supercluster formation in its infancy. By comparing these ancient regions to younger sections closer to us, scientists can trace how such structures grow, how delicate strands of galaxies condense into dense knots under gravity's patient pull. Every observation peels back another layer, revealing how the universe transforms chaos into order on scales that humble even the grandest human conceptions of size and time. So the next time you gaze southward on a clear night, remember, beyond the visible stars lies an architectural marvel of the cosmos, a gravitational masterwork where galaxies flock like starlings in flight, forever bound to each other in a dance set to the rhythm of the expanding universe. In the grand cosmic dance, galaxies aren't just drifting apart with the universe's expansion, they're caught in a mysterious current called the dark flow, a phenomenon so perplexing it might rewrite our understanding of reality itself. Picture hundreds of galaxy clusters, each weighing 1,000 Milky Ways, all streaming in the same direction at breakneck speeds, as if pulled by some invisible hand beyond the edge of the observable universe. This isn't just random motion, it's a coordinated march towards something we can't see, defying everything we know about how matter should behave on the largest scales. The discovery came when astronomers noticed something odd in the cosmic microwave background, the afterglow of the Big Bang. Certain galaxy clusters showed a subtle but consistent Doppler shift, their light slightly bluer in one patch of sky and redder in the opposite direction, as if they were all moving en masse toward a point billions of light years away. The kicker: this motion can't be explained by any known structure within our observable universe. It's as if the universe itself has a tilt, a cosmic incline causing everything to slide toward some unseen mass so enormous it warps the fabric of space-time from beyond our cosmic horizon. One radical explanation points to other universes. If our cosmos is part of a multiverse, a frothing sea of bubble universes born from eternal inflation, then the gravitational tug of a neighboring universe could theoretically explain this mysterious flow. Imagine two soap bubbles barely touching. Even through the thin membrane between them, the larger bubble might subtly distort the smaller one. In this scenario, the dark flow could be evidence of a parallel universe exerting its pull on ours, a gravitational whisper from a realm forever beyond our reach. Skeptics counter with more conventional theories, perhaps vast, undiscovered structures lurking behind the Milky Way's obscuring dust, or flaws in how we model cosmic expansion. But even these explanations push the limits of plausibility. To account for the dark flow's scale, any hidden structure would need to dwarf the Great Attractor by orders of magnitude, packing enough mass to sway thousands of galaxy clusters like leaves in a hurricane. The very possibility forces us to confront an uncomfortable truth. We might be missing entire chapters in the story of cosmic structure. What makes the dark flow so tantalizing is its potential to crack open one of physics' greatest mysteries, the nature of the multiverse. While parallel universes remain theoretical, this could be our first empirical hint of their existence, a shadow cast by something so colossal it defies comprehension. Future telescopes like the European Space Agency's Euclid mission aim to map this flow in unprecedented detail, hunting for subtle patterns that might reveal its source. Until then, the dark flow stands as both a cosmic anomaly and a beacon, a reminder that the universe, for all we've learned, still holds mysteries big enough to humble us all. At the cutting edge of cosmic cartography lies the Bootes Great Wall, a filament of galaxies stretching a mind-numbing 1 billion light-years across the universe, discovered not by spotting its glow but by listening to the echoes of the Big Bang itself. This cosmic behemoth gets its name from the Baryon Oscillation Spectroscopic Survey, a groundbreaking project that mapped the universe in 3 dimensions by studying subtle ripples frozen into the fabric of space-time. These ripples, called baryon acoustic oscillations, act like cosmic measuring tapes, fossilized sound waves from when the universe was a seething plasma soup, now stretched to unimaginable scales by 14 billion years of expansion. Here's how astronomers pulled off this cosmic detective work. In the universe's first few 100,000 years, matter and light were locked in a violent tug of war, creating pressure waves that reverberated through the primordial plasma like ripples in a pond. When the cosmos finally cooled enough for atoms to form, these waves froze in place, leaving an indelible imprint on how galaxies cluster. Fast forward to today, and by measuring the preferred distances between galaxies, typically around 500 million light-years, scientists can trace these ancient oscillations like breadcrumbs leading to hidden structures. The Bootes survey didn't just find a wall, it decoded the universe's birth certificate. What makes this wall extraordinary isn't just its size, it's how ghostly it appears in conventional telescopes. Unlike the glittering arcs of the Sloan or Hercules-Corona Borealis walls, the Bootes Great Wall reveals itself primarily through statistical analysis, a vast cosmic fingerprint detectable only when you plot millions of galaxy positions and spot the underlying pattern. Imagine trying to map a mountain range at night by only counting how often hikers cross your path. That's the level of ingenuity required to uncover this structure. The wall's most densely packed regions contain superclusters with names like the Sloan Digital Sky Survey Great Wall, but its true power lies in how it connects these titans into a single, coherent scaffold. This discovery reshaped our understanding of cosmic limits. The Bootes Great Wall flirts dangerously with what physicists call the end of greatness, the theoretical maximum size for structures in the universe. According to cosmological principles, at scales beyond roughly 1.2 billion light-years, matter distribution should smooth out into uniformity. Yet here we have a filament pushing right against that boundary, its very existence challenging models of how gravity structures the cosmos. Some theorists suggest it might be a statistical fluke, a chance alignment of smaller walls, while others see it as evidence that our universe's largest structures are even more intricate than simulations predict. Peering into the wall's structure offers a masterclass in cosmic evolution. Its galaxies aren't randomly scattered. They're meticulously sorted by mass, with lighter galaxies populating the fringes like foam on a wave while heavyweight clusters anchor the densest nodes. This segregation hints at billions of years of gravitational sorting, with smaller galaxies gradually ejected from crowded regions like pebbles shaken to the top of a jar. Meanwhile, the wall's sprawling voids, regions up to 300 million light-years wide, show how dark energy's repulsive force counteracts gravity's pull, carving bubble-like emptiness between the filaments. The real magic of the Bootes Great Wall lies in what it represents, a bridge between the universe's fiery origins and its present-day architecture. Those baryon acoustic oscillations it revealed aren't just artifacts. They're the universe's first vibrations, echoes of a time before stars or galaxies existed. By mapping them, we're effectively listening to the cosmos's earliest heartbeat, a rhythm now frozen in galactic distribution. Future surveys like the Dark Energy Spectroscopic Instrument promise to push this technique even further, potentially uncovering structures so vast they make the Bootes Great Wall seem modest. One thing's certain, as long as these cosmic echoes linger in the data, there will always be new giants waiting to be discovered. Embedded in the cosmic microwave background like a frozen bruise, the cold spot stretches 1.8 billion light-years wide, a region so mysteriously frigid it makes the surrounding universe look warm by comparison. Discovered in 2004 by NASA, a Wilkinson microwave anisotropy probe, this anomaly isn't just a minor temperature dip. It's a blistering puzzle that has astronomers questioning everything from the nature of dark energy to the existence of parallel universes. At its core, the cold spot defies simple explanation. While most cosmic microwave background fluctuations vary by mere millionths of a degree, this area is 70 microkelvins colder than its surroundings, a discrepancy so significant it should only occur once in 50,000 universes. One leading theory suggests we're looking at a supervoid, an enormous, mostly empty region of space where the lack of matter causes photons from the cosmic microwave background to lose energy as they traverse it. Imagine rolling a marble up a hill. In this case, the marble is light, and the hill is the gravitational well of the supervoid. As the light climbs out, it stretches, shifting to longer, cooler wavelengths. The problem: even the largest known voids are too small by a factor of 10 to explain the cold spot's dramatic temperature drop. If a supervoid is responsible, it would need to be so vast and empty that it challenges our current understanding of cosmic structure formation. Then there's the multiverse hypothesis, an idea straight out of science fiction that might hold the key. Some theorists propose the cold spot could be a cosmic bruise, left by a collision with another universe during the early moments of inflation, when our cosmos was expanding exponentially. In this scenario, the collision would have drained energy from that region of space, leaving behind an anomalous cold patch. It's as if our universe is a soap bubble floating in a froth of others, and the cold spot marks where we briefly brushed against a neighboring bubble. While this theory remains speculative, it's one of the few that can account for both the size and temperature of the anomaly without invoking unknown physics. But the plot thickens. Observations from galaxy surveys paint a conflicting picture. Some studies claim to detect an unusually sparse region of galaxies aligning with the cold spot, lending credence to the supervoid explanation. Others find no significant underdensity, suggesting the temperature anomaly might stem from something even stranger, perhaps a flaw in the statistical models used to analyze the cosmic microwave background, or an exotic interaction between dark energy and matter we don't yet comprehend. The cold spot refuses to yield its secrets easily, stubbornly resisting every attempt to fit it neatly into existing cosmological frameworks. What makes this cosmic enigma particularly tantalizing is its potential to rewrite the rules. If the cold spot does originate from a multiverse collision, it would be our first tangible evidence of realities beyond our own, a discovery that would dwarf even the Copernican revolution in its philosophical implications. Alternatively, if it's an unprecedented supervoid, it could force us to rethink how structures grow in the universe, revealing gaps in our knowledge of dark matter's role in shaping the cosmos. Either way, the cold spot stands as a humbling reminder. Even after mapping the afterglow of creation itself, the universe still holds profound mysteries that defy our best theories and instruments. Future telescopes like the Simons Observatory and next-generation cosmic microwave background experiments aim to scrutinize the cold spot with unprecedented precision, searching for subtle polarization patterns or secondary anomalies that might crack the case. Until then, this icy blot on the cosmic backdrop remains one of astronomy's most compelling open questions, a silent, frozen siren call, beckoning us to look deeper and question harder. The answers, when they come, might not just explain a curious cold patch, they could reshape our understanding of reality itself. In the celestial tapestry of the southern skies, where ancient navigators once traced the outline of a crane among the stars, modern astronomers have uncovered something far grander, the Great Wall. This 500 million light-year chain of galaxy clusters, named after the Great constellation it traverses, represents the final piece in mapping our local universe's largest structures. Until its discovery, our cosmic charts had a glaring blank spot, an uncharted territory hiding behind the Milky Way's obscuring disk, where dust and starlight conspired to block our view. But thanks to infrared surveys and innovative mapping techniques, we've pulled back the curtain on this galactic masterpiece, revealing a structure so vast it redefines our place in the cosmic web. What makes the Great Wall extraordinary isn't just its size, it's the way it completes the puzzle. Picture assembling a jigsaw where one missing piece leaves the entire image unclear. Before uncovering this wall, astronomers knew about northern giants like the Sloan Great Wall and the CFA2 structure, but the southern celestial hemisphere seemed oddly sparse by comparison. The Great Wall solved that mystery, proving the universe's architecture isn't lopsided, we just hadn't been looking through the right lenses. By combining data from the 2-micron all-sky survey with redshift measurements, researchers stitched together this colossal filament galaxy by galaxy, like reconstructing a dinosaur skeleton from scattered fossils. The wall's structure tells a violent, dynamic story. Unlike some relatively flat supercluster walls, the Great region twists through space in 3 dimensions, its galaxy clusters connected by tendrils of dark matter and hot gas. At its densest knots sit behemoths like the IC 1459 galaxy group, where elliptical galaxies dominate in a gravitational showdown, their stars locked in orbits shaped by ancient collisions. Between these clusters stretch vast bridges of hydrogen gas, cosmic highways where dwarf galaxies hitch rides on invisible currents. Some sections glow faintly with the X-ray fingerprints of superheated plasma, remnants of cataclysmic mergers that occurred when the universe was half its current age. What's truly remarkable is how subtly this wall affects our local cosmos. While structures like the Great Attractor pull nearby galaxies with obvious force, the Great Wall exerts a more delicate influence, its gravity gently steering the motions of galaxy groups millions of light-years away. Simulations suggest it might be connected to larger structures still unmapped, an appendage of some cosmic leviathan lurking beyond our current observational limits. This possibility hints at an even grander truth. The Great Wall might not be an endpoint in our mapping efforts, but a signpost pointing toward discoveries yet to come. For astronomers, this wall is more than just another entry in the catalogue of cosmic giants. It's a testament to how much we've overcome. The southern sky's obscuration by our own galaxy's bulk once made it astronomy's terra incognita, a blind spot hiding who knows what. That we've now charted it, painstakingly teasing signal from noise, speaks to the ingenuity of modern observational techniques. From radio telescopes piercing through dust clouds to space-based infrared observatories like Spitzer and WISE, each technological leap has peeled away another layer of the cosmic onion, revealing structures we once thought forever hidden. Yet for all its grandeur, the Great Wall carries a humbling message. Its discovery didn't just fill a gap in our maps, it reminded us how much remains unseen. Beyond this wall, beyond even the most distant structures we've catalogued, lie realms our current telescopes can't reach. Every time we think we've grasped the full scale of cosmic structure, the universe reveals another layer, another filament in the web, challenging us to look deeper, think bigger, and rewrite our textbooks once again. When astronomers first processed the Sloan Digital Sky Survey data revealing the Great Wall as DSS, it wasn't just the structure's staggering 1.37 billion light-year span that stunned them. It was how fundamentally its three-dimensional shape defied expectations. Unlike earlier discovered walls that appeared relatively flat when mapped, this behemoth twisted through space like a cosmic serpent, its galaxies strung along filaments that curved dramatically when viewed edge-on. Imagine crumpling a sheet of paper into a loose ball, then trying to trace a single unbroken line across its folds. That's the kind of complex architecture this wall presents on a scale that dwarfs even the most imaginative science fiction. What sets the Great Wall as DSS apart is its role as a celestial laboratory for galaxy evolution. Within its filamentary embrace, astronomers have observed something peculiar. Galaxies here mature differently than their counterparts in sparser regions. Dense knots along the wall's length act like cosmic incubators, where frequent galactic collisions trigger frenzied bursts of star formation, while the thinner bridges between clusters host older, quieter galaxies drifting in isolation. This stark contrast offers a real-time glimpse into how environment shapes galactic destiny, like watching trees grow differently on a mountainside versus a valley floor. The wall's discovery also forced cosmologists to confront an uncomfortable truth. Our simulations couldn't fully replicate it. Computer models of cosmic structure formation, based on the standard lambda CDM framework, consistently produced walls that were flatter and less intricate than what Sloan's telescopes revealed. This mismatch suggests gaps in our understanding of dark matter's behavior or the influence of dark energy during the universe's formative epochs. Some theorists now speculate that the wall's complex topography might preserve echoes of primordial quantum fluctuations, random density variations from the Big Bang amplified to cosmic proportions over billions of years. Zooming out reveals another layer of wonder. The Great Wall as DSS isn't an isolated structure. It's part of an intricate network that connects to other supercluster complexes, forming a sort of cosmic continental divide. Galaxies along its length exhibit coherent motion, streaming toward shared gravitational anchors in a slow-motion migration that will take billions of years to complete. Tracking these flows has become crucial for testing theories about the universe's large-scale dynamics, offering clues about how dark matter filaments guide galactic traffic across unimaginable distances. Perhaps most remarkable is how this wall tests the limits of observation itself. Because light takes time to travel, we see the structure's distant regions as they were when the universe was younger, meaning we're effectively observing its evolution in snapshots spaced billions of years apart. The far end appears more chaotic, with galaxies clumping in protoclusters, while the nearer sections show fully formed superclusters. It's like having a time lapse of city development, from scattered villages to bustling metropolises, all visible in a single gaze across the cosmos. As new surveys like the Dark Energy Spectroscopic Instrument map ever larger volumes of space, the Great Wall SDSS serves as both milestone and mystery, a reminder that even our most ambitious cosmic maps still have uncharted territories. Its very existence whispers a tantalizing question. If we can find structures this colossal in our relatively nearby universe, what unimaginable giants might lurk beyond the current limits of our view? In a universe teeming with colossal walls, filaments, and voids, there's a cosmic threshold where this intricate architecture supposedly dissolves, a point known as the end of greatness. Beyond roughly 1.2 billion light-years, the universe's grand designs are thought to fade into uniformity, like waves smoothing out into a still ocean. This isn't just a theoretical curiosity, it's a fundamental prediction of modern cosmology, rooted in the idea that matter distribution should become smooth at the largest scales. But here's the catch. Recent discoveries keep bumping up against this limit, leaving astronomers to wonder, are we missing something profound about the universe's structure? The concept hinges on the cosmological principle, which states that, on sufficiently massive scales, the universe should look roughly the same in every direction. Think of it like zooming out on a fractal. No matter how intricate the pattern appears up close, from far enough away, it blurs into homogeneity. This principle underpins everything from how we measure cosmic expansion to our understanding of the Big Bang's aftermath. Yet structures like the Hercules-Corona Borealis Great Wall and the Bootes Great Wall flirt dangerously with this boundary, stretching nearly as far as the supposed limit. It's as if the universe is teasing us, building right up to the edge of what we thought was possible before abruptly stopping. Or are we just not seeing far enough yet? What makes this frontier so fascinating is the tension it creates between theory and observation. Computer simulations of cosmic evolution consistently show that beyond the end of greatness, gravity's influence should weaken relative to dark energy's repulsive push, preventing matter from clumping into coherent shapes. But when telescopes peer into the deep universe, they keep finding hints of structure, statistical anomalies in galaxy distributions, unexplained correlations in quasar positions, and temperature fluctuations in the cosmic microwave background that suggest larger patterns lurking in the shadows. Some researchers argue these are mere statistical flukes, while others whisper about the need for new physics, perhaps modifications to how gravity operates at the largest scales or unseen forces sculpting the cosmic web in ways we haven't imagined. The real puzzle lies in how we measure this transition. Unlike nearby structures that can be mapped galaxy by galaxy, the end of greatness exists in a realm where light takes so long to reach us that we're essentially studying the universe's adolescence. The galaxies we observe at these distances appear as they were billions of years ago, meaning we're seeing the cosmic web at an earlier stage of growth. If structures appear more fragmented or uniform there, is it because we've finally reached the limit, or simply because gravity hasn't had enough time to finish sculpting them? It's like walking into an unfinished cathedral and declaring that the blueprint must be wrong because the arches aren't yet connected. This cosmic conundrum isn't just academic, it shapes how we interpret the universe's fate. If structures truly vanish beyond the end of greatness, it validates our current models, suggesting dark energy will ultimately stretch the cosmos into an ever more homogeneous expanse. But if future telescopes uncover coherent patterns beyond this scale, everything from our understanding of inflation to the nature of dark matter could be up for revision. The next generation of sky surveys, like the European Space Agency's Euclid mission and the Vera-C, Rubin Observatory's Legacy Survey of Space and Time, aim to settle this debate by mapping billions of galaxies with unprecedented precision. For now, the end of greatness remains both a horizon and a challenge, a reminder that even in a universe full of giants, there are still invisible lines we're only beginning to perceive. Whether it's a true boundary or just a reflection of our current observational limits, one thing is certain: the cosmos always finds a way to humble us just when we think we've grasped its grand design. While the Milky Way sits within the KBC Voids cosmic bubble, just beyond our doorstep lies another vast emptiness, the local void. This yawning chasm of nothingness, stretching 150 million light-years across, isn't just empty space, it's an active force shaping the motion of our galaxy and every star around us. Picture a cosmic game of tug-of-war, where the local void's lack of gravitational pull creates an imbalance, effectively pushing us toward denser regions of the universe like a ship drifting away from a dead current into stronger winds. What makes this void particularly fascinating is how it counterbalances the Great Attractor's pull. While that massive concentration of matter draws us inward, the local void's emptiness repels us outward, creating a delicate equilibrium that influences the Milky Way's trajectory through space. Astronomers call this the velocity flow of galaxies, a subtle but measurable drift caused by the competing gravitational influences of nearby structures and voids. Without the local void's push, our galaxy might be hurtling toward the Great Attractor at even greater speeds, altering the distribution of galaxies in our cosmic neighborhood entirely. The local void's impact extends beyond mere motion. Its presence has sculpted the architecture of nearby galaxy groups, creating what astronomers describe as a local sheet of galaxies, a relatively flat plane where galaxies cluster along the boundary between void and denser regions. Think of it like foam collecting at the edge of a draining sink. Galaxies naturally gather where the gravitational gradients are strongest, leaving the void's interior nearly barren. Only a handful of isolated galaxies, like the lonely UGCA 365, drift within its expanse, their starlight stretched thin across millions of light-years of emptiness. Discovering this void wasn't straightforward, because it sits almost directly behind the Milky Way's obscuring plane. Astronomers had to piece together its existence indirectly by mapping the peculiar velocities of surrounding galaxies and noticing a consistent gap in their distributions. It's like sensing an invisible pit by watching how surrounding objects roll away from it. Detailed redshift surveys eventually confirmed the void's staggering scale, revealing it as one of the dominant features in our local universe's gravitational landscape. But here's the twist: the local void might not be completely empty. Recent observations suggest it could contain faint, diffuse galaxies or dark matter filaments too dim for current telescopes to detect. If true, it would mean this void is more like a cosmic desert, sparsely populated but not entirely lifeless. Future instruments like the Nancy Grace Roman Space Telescope aim to probe these shadows, potentially rewriting our understanding of how emptiness functions in the universe's grand design. The local void serves as a humbling reminder that absence can be just as influential as presence in the cosmos. Its gravitational shadow doesn't just shape our galaxy's path, it quietly orchestrates the flow of our entire local universe, proving that even nothingness holds immense power over the fate of stars. Nestled in the constellation of Pisces, where ancient Hindu astronomers once charted the celestial river Saraswati, modern telescopes have uncovered a cosmic structure worthy of its mythological namesake, the Saraswati supercluster. This 600 million light-year behemoth isn't just another knot in the cosmic web. It's a relic from the universe's adolescence, a time capsule preserving the chaos of an era when galaxies first began assembling into the grand structures we see today. What makes Saraswati extraordinary isn't merely its size, it's the way its dozens of galaxy clusters packed together with gravitational intensity, forming a dense celestial metropolis that defies expectations of how such giants should evolve. Peering into this supercluster is like stepping into a cosmic museum. While most large structures we observe are still actively growing, Saraswati appears frozen in time, its galaxies having already completed their mergers billions of years ago. This unusual maturity suggests it formed during a period of accelerated cosmic evolution, when dark energy's influence was weaker and gravity could corral matter more efficiently. Imagine a city that built all its skyscrapers in a single frenzied construction boom, then paused while the rest of the universe caught up. That's the impression Saraswati gives. Its ancient galaxy clusters glow with the reddish hue of aging stars, their spiral arms long since smoothed into featureless ellipses by relentless collisions, while the supercluster's core harbors some of the most massive galaxies ever recorded, each weighing 100 times more than our Milky Way. The discovery of Saraswati challenged preconceptions about when such giants could arise. Standard cosmological models predicted that superclusters of this size and density shouldn't have existed until much later in the universe's timeline. Yet here it sits, fully formed when the cosmos was just 10 billion years old, a cosmic toddler by universal standards. Some theorists speculate that Saraswati might be evidence of primordial density variations far exceeding what our current models predict, while others wonder if it hints at undiscovered physics governing dark matter's behavior. Its very existence forces us to reconsider how quickly gravity could weave matter into such intricate patterns in the early universe. Mapping Saraswati's three-dimensional structure reveals even more wonders. Unlike flatter supercluster walls, this giant forms a roughly spherical swarm, with tendrils of galaxies radiating outward like spokes on a wheel. At its heart lies Abell 2361, a galaxy cluster so dense that its central galaxies orbit each other at speeds exceeding 4 million kilometers per hour, their trajectories bent by the combined gravity of hundreds of trillions of stars. Surrounding these crowded cores are vast reservoirs of hot gas visible only in X-rays that seethe at temperatures over 100 million degrees, heated to unimaginable extremes by shockwaves from ancient collisions. These turbulent seas of plasma stretch across millions of light years, threading through the supercluster like an invisible nervous system. What truly sets Saraswati apart is its role in the cosmic web's larger architecture. This supercluster doesn't exist in isolation. It anchors one end of a filament that connects to other known giants like the Pisces-Cetus complex, forming a bridge across the universe's scaffolding. Galaxies along this highway exhibit coherent motion, streaming towards shared gravitational anchors in a migration that will take billions of years to complete. By studying these flows, astronomers can trace how dark matter's invisible fingers guide the universe's growth, revealing the hidden skeleton beneath the visible stars. Yet Saraswati holds one final surprise. It's disappearing, not physically but observationally. As the universe expands, the supercluster's light stretches into ever redder wavelengths, eventually shifting beyond the detection range of our telescopes. Within a few billion years, it will vanish from view entirely, leaving only its gravitational imprint on surrounding structures. This impending cosmic fade-out adds urgency to its study, reminding us that the universe's grandest landmarks aren't permanent. They're fleeting wonders, visible only during brief windows of cosmic time, and Saraswati's window is closing fast. For astronomers, this supercluster is more than a record-breaking discovery. It's a key to unlocking the universe's teenage years, a turbulent epoch when gravity's grip first began sculpting matter into the vast structures we recognize today. Every galaxy cluster within it tells a story of violent mergers, galactic rebirth, and the relentless pull of dark matter. And as we continue to map its intricacies, Saraswati promises to reveal even deeper truths about how the cosmos organizes itself on scales beyond human imagination. Buried behind the Milky Way's dazzling starlight, where most telescopes see only an impenetrable glow, radio waves have peeled back the curtain on a hidden colossus, the Vela supercluster. Stretching 300 million light-years across the southern sky, this sprawling network of galaxy clusters remained invisible until astronomers cracked the code using an unlikely tool: the subtle wobbles of galaxies caught in its gravitational web. Unlike traditional surveys that rely on visible light, the Discovery team mapped Vela by tracking how thousands of galaxies mysteriously deviated from the universe's expansion, their paths bent by an unseen giant's pull. It's cosmic detective work at its finest, finding a monster not by its glow, but by the ripples it leaves in the movements of everything around it. What makes Vela extraordinary isn't just its size, it's its ghostly composition. While typical superclusters shine with the combined light of countless galaxies, Vela's core is eerily dim, dominated by vast clouds of dark matter weaving through faint, ancient galaxies. Picture a city where the skyscrapers are invisible, detectable only by the traffic patterns swirling around them. This missing light puzzle suggests Vela might be a rare, fossil supercluster, a relic from an era when the universe's structure was forming under different rules, its galaxies having burned out or drifted apart over billions of years. The supercluster's discovery hinged on a clever workaround to astronomy's greatest blind spot: the zone of avoidance created by our own galaxy's disk. Just as you can't see stars behind a spotlight, optical telescopes struggle to peer through the Milky Way's bright core, but radio waves slice through this cosmic fog effortlessly. By combining data from South Africa's Laniakea radio telescope with redshift measurements from the Anglo-Australian telescope, astronomers pieced together Vela's three-dimensional skeleton, revealing tendrils of galaxies stretching far beyond initial estimates. These filaments connect to known structures like the Shapley supercluster, hinting at a cosmic freeway system spanning nearly 1 billion light-years. Zooming into Vela's heart unveils a gravitational paradox. At its center lies Abell 3532, a galaxy cluster so massive it warps spacetime enough to create Einstein rings, distorted images of galaxies behind it. Yet surrounding this dense core are vast voids where galaxy counts plummet, some regions so empty they rival the Bootes void in sparseness. This yin-yang structure, extreme density bordering shocking emptiness, challenges theories about how superclusters evolve. Computer simulations struggle to replicate such sharp contrasts without invoking exotic physics, suggesting dark energy or primordial quantum fluctuations might have sculpted Vela in ways we don't yet understand. The real magic lies in what Vela represents, a new frontier in mapping the universe's hidden architecture. Traditional surveys have meticulously charted the northern skies, leaving southern celestial realms comparatively unexplored. As radio arrays like Laniakea and the future Square Kilometre Array probe deeper, they're revealing that many of the universe's largest structures might be hiding in plain sight, camouflaged by our own galaxy's glow. Vela isn't an anomaly, it's likely the first of many ghosts emerging from the cosmic shadows, each discovery rewriting our understanding of how matter organizes itself across the grandest scales. For astronomers, the supercluster serves as both a challenge and an invitation. Its very existence suggests our census of cosmic structure is woefully incomplete, with unknown giants potentially lurking behind every bright patch of Milky Way stars. Future missions like the Vera C. Rubin Observatory will tackle this blind spot by observing in infrared wavelengths, while gravitational wave detectors might one day map these structures by the ripples they create in spacetime itself. The Vela supercluster doesn't just expand our map of the universe, it reminds us how much territory remains uncharted, waiting for the right tools to bring it into view. While cosmic walls and superclusters dominate headlines, the microscopium void proves that emptiness can be just as fascinating. This sprawling spherical vacancy stretches 180 million light-years across the southern skies, a bubble so vast that if you dropped our Milky Way into its center, the next galaxy would be as distant as Earth is from the Andromeda Galaxy 50 times over. Unlike the Bootes void's near-total emptiness, microscopium represents a more typical void, containing sparse galaxies drifting like lone ships in an oceanic abyss. Yet its very normalcy makes it extraordinary. It's a pristine laboratory for studying how nothingness shapes the everything around it. Voids aren't just passive gaps, they're active players in cosmic evolution. Picture the universe as a loaf of raisin bread baking in the oven. As it expands, the dough space stretches, causing raisins' galaxies to cluster where the dough's gluten gravity is strongest, leaving empty pockets between them. The microscopium void formed through this exact process over billions of years, as gravity pulled matter into filaments and left behind these cavernous bubbles. But here's the twist: voids don't stay empty. Their repulsive effect creates what astronomers call void galaxies, isolated stellar islands pushed to the edges by cosmic expansion, like foam gathering at a wave's crest. What makes microscopium particularly intriguing is its maturity. Younger voids tend to be irregular, their edges jagged from recent gravitational tugs. But this void's smooth, spherical shape suggests an ancient equilibrium, a region where dark energy's outward push has perfectly balanced gravity's pull for eons. Infrared observations reveal its galaxies are predominantly red and aging, their star-forming gas long since stripped away by the void's harsh environment. It's as if the void itself acts as a cosmic desert, withering galaxies that wander too deep into its expanse. This void's most profound impact might be on the universe's expansion itself. Emptiness stretches space-time more dramatically than dense regions, creating what's known as void lensing, where the void's gravitational lack bends light like a concave lens, subtly distorting our view of galaxies beyond it. Future telescopes could use this effect to measure dark energy's influence with unprecedented precision, turning the microscopium void into a natural laboratory for probing the universe's ultimate fate. Yet perhaps the most humbling realization is this: voids aren't rare. For every glittering supercluster, there are dozens of microscopium-like voids weaving through the cosmic web. They remind us that the universe's true architecture isn't defined by where the light shines brightest, but by the delicate interplay between presence and absence, a dance of matter and emptiness on scales that forever redefine our sense of place. Hanging like a cosmic chandelier above Earth's northern hemisphere, the Draco supercluster weaves together some of the most studied galaxy clusters into a sprawling three-dimensional map of our local universe. Named after the constellation it dominates, this structure isn't one singular wall or filament. It's a complex intersection of multiple galaxy streams stretching 400 million light-years across, acting as both a landmark and a measuring stick for astronomers charting the cosmos' grand architecture. At its heart lies the famous Coma cluster, a dense swarm of over 1,000 galaxies so tightly packed that collisions happen frequently, stripping galaxies of their gas and leaving behind red and dead elliptical husks. Nearby, the Leo cluster adds another gravitational anchor, its galaxies orbiting a common center at speeds that betray the presence of staggering amounts of dark matter. Together with smaller groups like Ursa Major and Draco itself, these clusters form nodes in a web-like structure that helps trace the universe's hidden scaffolding. What makes Draco particularly valuable is its orientation relative to Earth. While many superclusters stretch across our line of sight, making distance measurements tricky, Draco angles diagonally through space, some sections closer, some farther. This unique alignment creates a natural ruler for testing three-dimensional mapping techniques. Astronomers can compare redshift measurements showing how fast galaxies move away from us with other distance indicators like supernova or galaxy brightness, refining our cosmic yardsticks in the process. It's like having a mountain range where some peaks are nearby and others distant, letting surveyors calibrate their tools across varied terrain. Peering into Draco's depths reveals unexpected patterns. Galaxy streams within it show peculiar alignments, their spins and orbits coordinated over scales that defy simple gravitational explanations. Some researchers suggest these filamentary alignments might be fossils from the universe's infancy, when spinning primordial gas clouds seeded galaxy formation. Others propose they're evidence of large-scale dark matter flows, invisible rivers sculpting visible matter over billions of years. The supercluster's outskirts add another puzzle. Galaxies here are moving faster than expected, hinting at gravitational pulls from unseen structures beyond our current maps. Modern sky surveys like the Dark Energy Survey have transformed Draco from a collection of individual clusters into a dynamic system. By analyzing how its galaxies move in relation to one another, astronomers reconstruct the supercluster's growth history, how small groups merged into clusters, then into this immense structure. Computer simulations now suggest Draco is still accumulating mass, with new filaments of galaxies falling into it along paths predicted by dark matter models. These virtual reconstructions align strikingly well with observations, validating our understanding of cosmic evolution while leaving room for mysteries, like why certain regions have fewer dwarf galaxies than simulations predict. For stargazers, Draco offers a humbling perspective. On clear northern nights, amateur telescopes can spot fuzzy patches marking the Coma cluster's brightest members, each smudge containing hundreds of billions of stars. That visible light left those galaxies when Earth's mammals were just emerging, traveling through space while continents shifted and civilizations rose and fell. Yet even these ancient photons show us the supercluster as it was relatively recently, a nearby structure that continues shaping our local universe's fate, its gravity gently steering the Milky Way's path among the cosmic currents. If the cosmos has a gravitational capital, a place where matter gathers in almost unimaginable density, the Shapley concentration would be its Times Square at rush hour. Located 650 million light-years away in the constellation Centaurus, this sprawling metropolis of galaxies represents the single most massive structure in our nearby universe, a gravitational vortex so powerful it pulls thousands of galaxies toward it, including our own Milky Way. Imagine a cosmic grand central station where entire galaxy clusters, each containing thousands of galaxies, converge into a dense supercluster of superclusters. The numbers defy comprehension. At least 25 massive galaxy clusters anchored by titans like Abell 3558, their combined gravity sculpting spacetime into a well so deep that light itself bends around it. The sheer concentration of mass here is staggering, equivalent to 10,000 Milky Ways packed into a region just 30 million light-years across. This isn't just a cluster, it's a gravitational empire dominating the dynamics of our local universe with the subtlety of a black hole in a china shop. What makes the Shapley concentration truly extraordinary is its influence. While the Great Attractor steals headlines as the mysterious force pulling our galaxy, it's increasingly clear that Shapley is the mastermind behind the curtain. Our entire local group, along with the Virgo supercluster and the Hydra Centaurus region, are caught in what astronomers call the dark flow, a vast river of galaxies all drifting toward this distant gravitational overlord. Current estimates suggest Shapley's pull accounts for nearly half our galaxy's peculiar motion, dragging us toward it at 700 kilometers per second despite the universe's expansion trying to push everything apart. Peering into Shapley's core reveals a scene of cosmic violence. X-ray telescopes like Chandra capture vast clouds of superheated gas, some reaching 100 million degrees, shocked into searing brilliance by relentless collisions between galaxy clusters. These merging behemoths release energy surpassing 1 trillion supernovas, sending shockwaves through intergalactic space that can strip smaller galaxies of their gas, leaving them barren and starved. Yet amid this chaos, Shapley exhibits eerie organization, its clusters arranged along filaments that trace the invisible scaffolding of dark matter, a hidden architecture guiding visible matter into place like iron filings on a magnet. The concentration's discovery in the 1930s by Harlow Shapley was just the beginning. Modern sky surveys have revealed its true scale, a structure so vast it spans 24 full moon widths in our sky despite its immense distance. Its gravitational reach may extend even further, with some theories suggesting connections to the Horologium Reticulum supercluster and other distant giants, forming a supercluster complex that could rival the size of the Sloan Great Wall. If confirmed, this would make Shapley not just a local heavyweight but a nexus in the cosmic web's grandest highway system. Yet for all its dominance, Shapley holds an unsettling lesson about our cosmic perspective. From Earth, it appears as a relatively modest smudge of light, a reminder that the universe's most powerful structures often hide in plain sight, their true nature revealed only through painstaking observation. Future telescopes like the Vera-C, Rubin Observatory promise to map Shapley's outer fringes, hunting for faint galaxies or dark matter streams that might explain its gravitational grip. Until then, it remains both anchor and enigma, the silent giant remapping our corner of the cosmos one galaxy at a time. At the edge of our observable universe lies a cosmic anomaly so baffling it has astronomers debating the very foundations of modern cosmology. The cold spot in the cosmic microwave background, paired with an alleged supervoid spanning 1.8 billion light-years. This eerie alignment presents a cosmic riddle. Is this vast underdense region simply letting light lose energy as it climbs out of a gravitational valley? Or are we staring at something far more exotic, perhaps even evidence of a parallel universe brushing against our own? The cold spot first made waves when satellites mapping the afterglow of the Big Bang noticed a peculiar chill, a patch 70 microkelvins colder than its surroundings, spanning an area of sky 5 times wider than the full moon. Such fluctuations normally vary by mere millionths of a degree, making this anomaly statistically improbable, like finding a single ice cube floating in a steaming ocean. Initial explanations pointed to the integrated Sachs-Wolf effect, where light crossing underdense regions supervoids should lose energy, stretching to longer, cooler wavelengths. Sure enough, redshift surveys later identified the Eridanus supervoid, a sparse region aligning roughly with the cold spot's position. Problem solved. Not quite. Here's where the plot thickens. The supervoid's gravitational influence is far too weak to account for the cold spot's dramatic temperature drop by a factor of 10. It's like blaming a pebble for creating a Grand Canyon-sized dent. Some theorists argue the void might extend beyond current mapping, its true dimensions hidden by observational limits. Others propose more radical solutions, like cosmic textures, hypothetical defects in spacetime from the universe's early moments, or even collisions with another universe during cosmic inflation. Picture 2 soap bubbles briefly touching. The energy drain at that contact point could leave behind a cold imprint visible billions of years later. The debate exposes a deeper tension in cosmology. If the supervoid fully explained the cold spot, it would imply voids grow far larger and emptier than simulations allow, forcing revisions to how we model dark matter and dark energy. Alternatively, if no void can account for it, we might need entirely new physics, or accept that we've glimpsed a fingerprint from beyond our cosmic horizon. Future telescopes like the Simons Observatory aim to settle this by measuring the cold spot's polarization patterns, hunting for telltale signs of exotic origins. What makes this mystery so compelling isn't just its scientific stakes, it's the philosophical vertigo it induces. The cold spot challenges our assumptions about the universe's uniformity, whispering that even our most careful observations might be showing us only a fraction of reality. Whether it's a mundane void exaggerated by chance or a crack in the cosmic egg revealing a multiverse beyond, one thing's certain. This frigid anomaly continues to freeze cosmologists in their tracks, its true nature as elusive as the distant glow it's written in. Standing here on our pale blue dot, it's almost impossible to fully grasp the immensity of these galactic titans. We've explored structures so vast they make entire superclusters look like specks of dust in the cosmic wind. From walls stretching billions of light years to voids so empty they defy logic, the universe has shown us architecture on scales that shatter every human intuition about size and distance. These aren't just scientific curiosities, they're reality checks, humbling reminders that the cosmos operates on a playing field where even our most ambitious metaphors fall short. What's truly revolutionary isn't just their size, it's how these structures force us to rewrite the rules. Every time we think we've understood the universe's limits, discoveries like the Hercules-Corona Borealis Great Wall or the cold spot come along, tearing up our cosmological playbook. The very existence of these formations challenges fundamental principles we once took as gospel, like the idea that matter should distribute evenly on the largest scales. Instead, we're finding a universe that prefers wild, intricate designs, where emptiness and density dance in patterns we're only beginning to trace. Consider what this means for our place in the grand scheme. Our Milky Way, with its hundreds of billions of stars, is less than a grain of sand in the Sahara of the cosmic web. Yet here we are, a species that evolved on a rocky planet around an ordinary star, somehow able to map these impossible structures, to measure their shadows across billions of years, and to question how they came to be. That paradox alone is worth pausing on. Tiny, fleeting beings decoding the blueprints of the universe's greatest monuments. This journey through cosmic architecture isn't just about satisfying curiosity, it's about perspective. When faced with structures older than Earth itself, where light takes millions of millennia just to cross from one end to another, our daily worries shrink to their proper scale. The universe doesn't care about borders or budgets or social media feeds. It builds and destroys on timelines we can't comprehend, in spaces we'll never physically reach, yet we're privileged to witness even a fraction of its grandeur through our telescopes and equations. For those hungry to dive deeper, the adventure is just beginning. Each of these cosmic giants we've explored is a doorway to a dozen more mysteries, questions about dark matter's hidden scaffolding, about parallel universes that might leave gravitational fingerprints, about the true nature of the cosmic web's ghostly threads. The night sky isn't just a scattering of stars, it's an infinite puzzle box waiting to be unlocked, one revelation at a time. So the next time you find yourself under a clear night sky, remember, you're not just looking up. You're peering into the universe's deepest archives, where every faint smudge of light tells a story older than time itself. The greatest discovery isn't any single structure we've found. It's the realization that no matter how much we learn, the cosmos will always have new wonders to reveal, new scales to astonish us, and new mysteries to keep us forever staring upward in awe.